Welcome to part 4 of Seeing Birkeland Currents. In this episode, we'll be discussing the Radcliffe wave and the implications that this has for the Gould belt. We will also discuss how we think the Gould belt formed and how this potentially fits into the larger structures that surround us. So lastly, the Radcliffe wave. So for me, this, and we sort of talked about it anyway, but for me, this sort of confirms that idea that we've talked about when we looked at some of these other images, you know, of the fact that you have a complex Birkeland current, which has these shells within it, and we are in this image. What they are mapping is part of a much larger structure. But what was your take when you sort of saw this article?
Well, again, I had been predicting for a while that they would find a helical stream around the arms, just because locally the Pleiades stream matches what we would expect of a helical stream. It's just that we lose it when we're far from the galactic plane. We can't see it really. But when I saw that image, that's what I thought that they were even going to say, is that this was a helical stream around the arms, but they just see it as going up and down. And the irony, though, is everywhere in space, I mean, they see, however they want to explain it, they see helical structures, the double helix nebula and, smaller scale Birkeland currents. So it struck me as odd that they just want to make it a purely up and down motion when they don't see that. They don't really see that anywhere else. So, well, you can understand though how when you see how they map that they might be seeing a helical structure just from the side, and then just since they don't have a mechanism for that, then they just want to make it an up and down way, because that's how it appears from our.
I've seen, explanations that effectively what they think is that another galaxy came close enough with this particular part of the Milky Way arm, and therefore caused this sort of like a wave pattern to be sort of frozen into that structure of the arm because of that close sort of collision proximity. I don't know. I mean, where that galaxy is now gone is beyond me, because it must have magically vanished.
That's the same issue they had. See, they're just resurrecting the idea of how they thought the Gould's belt was formed in the beginning, or the Pleiades stream that's coming through was the same way. There's got to be this chunk of matter, either something that we could see, or in the case of with Gould's belt, what they wanted to do was make it dark matter. And first, the original explanation for that belt was that there was dark matter in the galaxy right now that would explain the rotation of that ring of stars. But then that didn't work out, because you would also have to explain the rotation of other stars, or the lack of rotation of other stars around that. So then they moved it onto, a clump of dark matter crashed through the galactic plane, and that's what formed that. And then that clump of dark matter continued on, and we don't see it anymore. But then that doesn't explain why the belt right now is rotating. It doesn't. A clump of dark matter crossing through the galaxy might have explained the formation of that ring, but then it doesn't explain why that ring is bound and rotating now. So that also didn't work. And that's really what they're trying to get rid of. They don't have a theory for how you can have a ring of stars rotating as a ring without enough mass there. Especially since they can't make dark matter work in that case, they just want to throw away the whole structure. So that's what they're trying to do, basically.
Sweep it under the carpet.
Right.
Can't explain it. Let's just get rid of it.
Yeah. Right. Exactly. But that's absolutely not right. And that structure is real, and that's why we really got to count on people. in the mainstream, the ones that have mapped that out, that rotation, it's important to understand the history of that ring. Is that anyone can go out in the night sky and look out at the night sky and see that there's this ring of bright blue stars. Well, the mainstream did is they measured the distances and found out that, yeah, it's kind of a ring. And then when they expected to see it expanding, the idea was that it was formed by a supernova in the beginning. They started looking closely at the stars and found out not just that it is slightly expanding, but it's also rotating. And that's the part that you can't explain in the gravity only model. So, like, why should this ring of stars be rotating as a ring if there's not enough matter to hold it bound to that center? You can't just have things circling around nothing. So
they can't.
Right. so they just want to have it. They just want to sweep that under the rug. So now they're seeing the structure, and the important thing to realize is, yes, they can map the positions of stars to that, but they still have to explain that rotation. And that's where I'm hoping other people in the mainstream, the ones that worked really hard on mapping that star motion and rotation, that they'll see that Radcliffe wave idea isn't going to help them there. It's not going to help them to explain why we see stars on one side of the ring rotating around, then we look out on the other side and still seeing rotating around. That's not going to be present in their model of this more or less up and down bobbing wave. It's just not going to be there. So
yeah, I mean, even if you look, so this is the data from their analysis, and that's the sun, the orange one at the center, and the ring that you see is the Gould belt. And obviously what they're trying to say is that it doesn't really even line up that well, but that this is effectively an optical illusion from where we sit, that actually it's replaced by other things. But you know, it's in both directions. So again, I guess what they're trying to say is that some of these gas clumps behind it would form part of that ring. But I think, as you said, it doesn't really explain the motion, nor the fact that they are all blue stars. You know, there is something special about that that belt, important in terms of the overall structure. And I think that when you look at this shape, what kind of is missing from their initial analysis is the fact that, yeah, they might well be right that this does indeed trace what we would see as a filament, but what you don't really see is that actually there is within that model another one. And this is where Chris actually helped me. He did the modeling, the 3D modeling in the video. Let's see if I can just pull it up quickly. Cosmic wave, because there we go. So that's, I mean, I kind of talked him through, and he just sort of ran with it and then pulled it together. But I think it nicely illustrates the fact that you could actually see it as a pair of, if you looked at some of their data. So they have some of it there, but actually, depending on how you draw it, we could see actually two pairs of filaments, one coming down and one going up and across. And, you know, this by no means is this the only bits of data, which is, you know, what you were talking about, the fact that, you know, there are other structures that we found and mapped, you know, the ones with the, let me just jump to that image.
Yeah, see, if we're looking out at that Radcliffe wave as like the red image there, what we could view as our filament that we're in, that we're not seeing, is the blue one, and the Pleiades stream would be coming down across with a Gould's belt wrapped around it, and then we're looking out at the other filament, basically, the other helical filament. So
yeah, so that's why you see the Gould belt in there, in this one, sort of lines up. So the other filament that we would be on would be coming down and through here, so crossing over.
And the important thing is that the mainstream sees a stream of blue stars coming down right through the center of that. So that's, you know, there's So it's not arguing that they don't see that other stream over there, but that they, they're not mapping ours. They're almost forgetting that we already know that there's a stream of stars coming right down through the middle of that one.
Yeah, it's being convenient with the truth, economical with the truth.
Right.
Because it doesn't fit their data. You can't have two waves, because that would break their argument, because their argument has to be that this Radcliffe wave carries on across the entirety of our arm. If it is caused by a collision, you would expect to see, it might undulate a little bit, but you would expect that wave structure to hold across the length of that arm, rather than what we're proposing, which is
right.
a set of structures that are twisting helical structures.
Right. And again, the problem, they can't see the three-dimensional part of it too, because we're close enough to it, but we're not, we are off to the side of it, but we're not going to obviously see we have advantages, like for like a structure like the double helix nebula, you can actually see that the filament crosses in front. One filament crosses in front of the other and then disappears behind it. You know that that's a helical structure. They don't have that luxury here of seeing how that basically the three-dimensional shape that this is caused by. They're just getting the sight lines down. Basically, that's it.
Yeah, which is very obvious when you look at this data here, that it is based on a line of sight. And I guess that's part of the problem as well, is mapping some of these structures in 3 dimensions is incredibly difficult to do, and even mapping a distance to a star, that is relatively close to us, is extremely difficult to do. So working out the positions of all of these things, there is a margin of error that gets larger and larger the further you are away from where we are.
Right. Yeah, that's one thing that's not. I mean, the mainstream kind of tries to sweep that under the rug too. When they give you these pictures of like what interstellar gas clouds or look like, but all you have to do is, if you look up pictures of, for example, the local interstellar cloud, you might see 3 or 4 artist renditions that look totally different. One will look like a nice smooth line, others look like braided filaments, and the truth is they're just guesses based on a few sight lines, and the key to understanding that is, all we can really see, like with dust clouds, is you look at, for example, that's one. It gives you this idea that we're on this nice, pretty much curving gas cloud, but you can find other images of the local interstellar cloud that looks more like braided filaments between us and Sirius, for example. And all these are just artist depictions based on what we know from some sight lines. But as you can see here, we can see how much dust there is between us and Sirius. We can see how much dust there is between us and Altair over there, or Alpha Centauri. But there's not a whole bunch of stars scattered around in there. So all they can do is look at those sight lines, and yes, more distant stars, but then for more distant stars, there will be all along those sight lines. In other words, it's really hard to get a 3-dimensional map. All you can see is that, yes, looking at this star, there's gas between us and that, or dust between us and that, or a magnetic field between us and that. And that's, then they have to build up the whole 3-dimensional picture. But as you can see, that's really hard. It's actually harder on the more local scale, because we have fewer light sources. If you start moving outwards, you can actually get a little bit better map, because on any sight line, you'll have more and more stars to work with. But that gives you the biggest problem. That's what I had when I started researching these ideas of these being Birkeland currents, is that so much of the mainstream picture was going by what they knew that these things were in their opinion ahead of time. They know these are shock fronts from, exploded supernova, so they know what shape they're trying to make it match, and all their pictures then go with what they think they're seeing. But it's actually that's not always what the data says.
Yeah.
But as long as everybody's just aware that when they see these pictures, that's not exactly what they're seeing. That's what they think they're seeing based on.
Well, I mean, it becomes a little bit clearer when you look at this. I mean, this is basically even this their ability to map exactly where these dots are, these lumps of gas, is based on having some star that sits in front of it, so that they can tell where the edge lies. And I presume these are actually error bars that they've drawn in on some of those.
And that points to the problem. Notice that the error bars are huge along the line of sight, not yes. You have no trouble figuring left to right across the sky where it is, but how far on that sight line? And notice that those error bars are pretty significant. You could even if they're right about those, you could map some significant helical motion onto that. So.
Yeah, and then when you look at these sorts of these sorts of images, I mean, this is just, it's our best guess based on, as you say, the fact that they think that it was a supernova that caused it, so therefore it must follow this shape. But obviously, from where we sit, we have limited visibility of some of these things, and that's probably hard for people to sort of visualize and picture. That means making and understanding how these things fit together, extremely difficult, because we are kind of stuck where we are.
Right.
In part 5, we'll be discussing the local interstellar clouds and how we fit into the picture of the movement of these clouds and our local stars as well. As always, be brave, be curious, the truth is waiting for us. Until next time.